Hello everyone, and welcome to the sixth tutorial of this video series, in which we're going to be looking at variables and data types, as well as a couple of other things such as relations and operations within the Python programming language. During the fifth tutorial, we've already discussed the Boolean data type, which basically just comes down to true and false. And so let me just explain what this reset does. It just allows us to clear all the variables from the memory of the kernel, all right? Or we can actually, depending on whether we have declared the variables, say x was declared as false or whatever, and then you want to print x, but if I delete x by running this command, then x is no longer available, all right? So that's something that to keep in mind throughout this discussion, where we might use the same variable name throughout for different types of variables. All right, so let me just get rid of that, and then below make a new line. And I just want to remind you of what the Boolean variable is. It's just basically a value that is either set to true or false. All right, and so I've also taken the liberty of including the type operator, which is a built-in operator to Python, which takes as argument the variable itself. We've declared the variable x over here, then I've actually printed the variable x to the console, and then I actually want to get the type as well, which gives it to me in a class format. So basically that's just because Python is an object-oriented programming language. So it says print type of x, and it returns the class boolean. Right. So that's one of the type of variables that we can have. We can also have texts or strings, and to illustrate how to use that, let's just clear the variable x. So x is no longer set to anything. And then I want to actually write a sentence. This is string. And then I want to print x. And I also want to print or find the type of x. Although I know it's going to be a string. Just want to illustrate that explicitly to the screen. Alright, so it says string, right? There are many other types of variable data types. In this next example, I will be illustrating to you the numerical data types, such as, for example, integer. Now, you do not necessarily need to declare that as an integer. You can just write x equals 5, and then we can still print x, and we can still print the type of x, and automatically Python should know that it's an integer because, you know, it looks like an integer. But we could have also taken x to be the integer 5, and still it picks it up as an integer. But yeah, as I said, it wasn't necessary to declare it as such. So yeah, let me just clear x again. The other types of numerical data types that we can set a value equals to is, for example, a float value, but that really just comes down to a decimal value, right? And we just call it a float value in terms of computers, because that is a specific technique that is used to simulate how the real numbers in mathematics work, you know, but there is really no actual way of defining a real number in a computer. Okay, so, but we'll talk about that much later and so on. So this is just introductory stuff. So if I don't declare it as a floating point number, then, you know, as in the previous example, it is still understood by Python that this is a float data type, right? So that's going to give me float, but I could, as I said, still declare this as float. That process is actually called casting, all right? And it just basically takes the number and it makes sure that it is associated to the correct data type, all right? That process of including the data type declaration in front of the number itself in brackets, right, like that. So the next data type that we're going to be looking at is lists and tuples, and so the difference will become clear once we've explained what a list does and what a tuple does. So if we look at a list as an example, I've just included this list, which is indicated by the use of square brackets, and basically it just includes 3 names. I can also include numbers, for example 5, and I may repeat values. So for example, perhaps I want to repeat the value Joe, but the exact same spelling and everything. If I print that to the screen, it's just going to give me back the list. So what's important is the way that we can then access values in this list by using the name of the list, right, x in this case, and then referring to the index. So naturally in most programming languages, the first index value is at 0, as the natural numbers start at 0, and then increment with 1 each time. So x0 should return the value Bob, right? And the value x square bracket 1 should return Rob. Okay, and so forth. So the thing about lists is that we can actually change the value in a list by just assigning a new value to it. Perhaps I want that to be Jane. Let's just print the entire list. And you should get Jane, Rob, Joe, 5, Joe, right? And it returns all those values in the same way except for the one that we've changed. But the difference is that if this were to be a tuple, which works in the exact same way except for the fact that the brackets are round. Those are brackets, these are braces, right? Alright, so basically this is the same concept except for the one difference that I cannot change in any of the values or in the entries within the list. So if I wanted to make this Jane, it's just going to give me an error and say that it's a tuple, and a tuple does not support the item assignment. Alright, so there's nothing that I can really do about that. If I want to change anything, I have to use a list or some other data type that allows me to do this, right? But yeah, as I said, we can still access the value x at index 0, but it didn't change to Jane in this case. Alright, so that's interesting. Other data types that I might want to use in Python includes dictionaries. In this case, this is what a dictionary might look like. Often it's referred to as a key value pair, and so basically it just associates a key, in this case Bob, with the surname, in this case Dylan, and Rob with Zombie, and Joe with Rogan. These are key value pairs, right? If I want to return that list, I'm going to get Bob, which is associated to Dylan. I'm going to get Rob, which is associated to Zombie, and Joe, which is associated to Rogan. And now if I want to refer to any values in this list, I'm still going to use the same method as before, except now I can't use indices. I have to use the key to access the value. If I wanted to refer to Rob's surname and return that value, I can just type the name of the data structure, in this case the dictionary X, and then in the square braces type the key, and it will return the value Zombie, and so on and so forth, right? Another data type that is quite useful is something we've kind of already looked at differently, though not in the context of Python, is sets. And so sets, what's really crazy about them is that they're not ordered at all, and they're unchangeable, and they're unindexed. So really they're just sets, literally by the mathematical definition of a set. Alright, so it's just going to give me Rob, Joe, Bob. And so you can see it actually, or no real order in fact, it just did its own thing. As you can see, there is no way of referring to the index to the item inside of a list. Set object is not subscriptable. That's the error that it gives me. Alright, so that's interesting and everything, but we need a hell of a lot more to start to be able to start doing some code. So we're going to look at the next concept within Python, and that is what is normally referred to as relations, but often it is incorrectly referred to as comparison for some reason. And basically what this comes down to, if you are given a set, then the relation, capital R, over this set is a subset of ordered pairs. That means maybe they come together as 2. We're really just restricting ourselves to binary relations. That means taking 2 elements, or in this case greater than, less than, and so on. So yeah, given a set X, a relation R over X is a subset of ordered pairs of elements from X. And as you can see here, this expression here, the set builder notation just really says that R is a subset of the tuples of X and Y from X. And the statement XY in R, the tuple XY in R, can be interpreted as saying that X is R related, usually written with infix notation X or Y. Here's a couple of examples of some relations, and so the most obvious one would be something like this, that if Jacob Dylan is the son of Bob Dylan, and then if we allow small j and small b to be Jacob and Bob respectively, then we can use infix notation to denote this by saying that J capital SB can be interpreted to mean that Jacob is the son of Bob, right? But I want you to notice that this relation is not symmetric. What that means is that we cannot swap the B and the J in opposite order to say BSJ, because it's not true that Bob is the son of Jacob, right? So we have to be really specific when we talk about relations. And some more obvious relations that you surely are familiar with from like school level and stuff, which would include stuff like the less than relation where 1 is less than 2, or 3 is less or equals to 3, or 5 is greater than 4, and so on. But we also have the ability in programming languages where we can check if strings are actually equal. So this is an equality relationship, but this is really more specifically a test for equality. So this is where I'm saying 8 is equals to 8, but I'm checking if that's the case. And here I'm saying string is equals to string. I have this double equality here, which means I'm checking if that is the case. And so the opposite to that would be not equals, as in 8 is not equals to 9. That's 8 exclamation equals 9. Another more unfamiliar but still quite common relation that we might encounter is something like divisibility, as in 3 divides 9, but 9 does not divide 3. Okay? Here's a more abstract relation that we may discuss quickly in terms of set builder notation. So A is the set 9, 16, 25, and B, as you can see, is like literally the roots of those integers over there. So the relation is, in this case, I've defined this set S, that X is the square of Y, right? Where X is from A and Y is from B. So we can see that there's two ways of writing this. I mean, I've already explained to you the infix notation, which is 9s3. That means 9 is the square of 3, but we can also write it with this prefix notation. 9, 3 is in the relation S. In other words, 9, 3 belongs to the subset of the Cartesian product A, B. And so, why is that useful? Well, I mean, relations come up about everywhere, especially in databases and in some Lambda calculus, which is something that I think we're going to be discussing much later than this tutorial. But just to get you started, we really want to be able to do some programming. And for programming, like basic programs and stuff, we really do need simple relation symbols, especially like greater than, less than, right? So a good example here would be to say that, okay, we're going to test that if 2 is greater than 1, please print true, otherwise print false. So you can see that because that's true, the code has returned the value true, right? And it just skipped over the else part. Here's another example, which is pretty much as obvious as the previous one. And in this case, it's going to print false. Here I have another example where I have greater or equals to 1 compared to itself with the relation greater or equals to. It's obviously going to return true because it is equals to itself, isn't it? But as we all know, if I compare 1 with itself with the relation symbol and strictly greater than, no equality, then of course it has to return false. Okay, we can also, as I said before, we can check for equality by using the double equal symbol. So if 1 is equals to 2, which it isn't, then return true, otherwise return false. Okay, and so that's as expected. And the nice thing about programming, as I said before, we can also compare different data types. In this case, we're going to compare two strings, and because they are equal, all the letters are capitalized in the same sense, in the same way. That should return true. But in my next example, I intentionally changed the capitalized S for the second string just to prove that it will return false. Okay, that's also expected. So yeah, as I said, relations and maths are quite interesting, but a lot of what's going on in relations and a lot of the maths over there is really complicated, and we shouldn't really concern ourselves with too much of the detail to be able to do some simple programming. But just for interest's sake, let's go through these cells quickly. Okay, so obviously relations have different properties. We saw that greater than and equals to versus just greater than behave in a way different manner, right? So greater or equals to actually has this symmetric property, but less than or greater than, they don't actually have that reflexive property. And what I mean by that is, it just really satisfies this axiom over here that a element relates to itself. So for example, it is true that 1 is equals to 1, and it's also still true that 1 is greater or equals to 1, but it's not true that 1 is greater than 1, right? So that reflexivity doesn't hold. And so you can go look at all those properties on your own a little bit in depth, or you might actually explore those in a better written course later on, right? But as I said, we can go on for the remainder of this tutorial and just speak about relations, but I think that would really just be beyond of the scope. So I just wanted to get you the basics so that we are capable of writing some much more fundamental programs that you may be able to use in your profession or whatever you want to use this for. So next up, we're going to look at our operations, and what I mean by that is stuff like addition, subtraction, and so on. But yeah, just to remind you, I think this is quite often ignored when introducing the concept of operations, is that a set of elements, x in our case, is said to be closed. And so this is the idea of closure under an operation. So a set of elements, x, is said to be closed under an operation if for any two elements, say you take two elements, it could be 1 and 2 from the natural numbers, it could be two real numbers from the real number set. But in this case, let's just take a and b from x. And the algebraic result a star b, because remember star is our operation, then a star b must be again in the set for us to be able to say that x, the set, is closed under that operation, right? So we all know 1 plus 2, equals 3. And since 3 is in the natural numbers, we know, since this is true for all natural numbers, the natural numbers is closed under addition, right? So keep that in mind when we go along. But we can also do this with like decimal values, floating values, and whatever. So this is just the basic idea of addition, So addition is quite fundamental, and that actually brings me to the next point, is that we can define multiplication in terms of more fundamental operation. What I mean by that is that multiplication is just repeated addition, division is just repeated subtraction, exponentiation is just repeated multiplication, and so on. So we can use this more fundamental operation, which you can define in terms of the successor function. It's quite interesting, but I think it goes way too much into detail for us to discuss in this tutorial once again. So I just want you to understand that we can use the more fundamental operations to define the more complex operations, but we don't have to do that because Python has all of this built into its language. So we can just go ahead and use them as they are provided to us. We can kind of assume that subtraction is a part of Python. We can kind of assume that multiplication is inside of Python. So we don't really need to go and redefine each and everything. So over there I've done multiplication of 2 and 3. I'm now going to multiply 2.2 and 3.3, which gives me this as a result. I can actually also exponentiate 2 to the power of 3. And so this is actually a nice one that I just want to talk about it a little bit more. So here we have star star, where that is directly associated to like multiplication. This is actually telling me that I'm defining exponentiation as repeated multiplication. So that's multiplication, and that is over there is exponentiation. That's 2 to the power of 3. Okay, I can also raise to half powers, or non-integer power. So 4 to the power of a half, as we all know, that's basically corresponds to the square root of 4, which is going to give us 2, right? 2.0 is going to return this floating value because I've included 0.5 over there. Okay, but there is also a built-in package that can do that for me. So if I import the math library into Python, I can say math.square root of 4, and obviously that's going to give me 2. I would just prefer to just write 4 to the power of 0.5 because I know that the square root really is just a half exponent, right? So I can actually just avoid using any library there. Alright, so the next thing we're going to look at is division. So that's division over there. That's 6 divided by 3. We also have, well, as an example, 7 divided by 2, which is obviously 3.5. We can have more exotic values like 8.1 divided by 3.3. That gives me a recurring value. Alright, but there's also this more interesting modulo operator, which I think you might encounter a couple of times. This one really goes back to Carl Friedrich Gauss, and maybe some people just before him, like legit, So Carl Friedrich Gauss came up with this modular arithmetic, where 4 divided by 2 is obviously 2, but we're looking for the remainder, and so there is no remainder, and it should just return 0. Okay, what would your best guess be for 5 modulo 2, since the modulo operator basically just returns the remainder of the division of 5 divided by 2. So the remainder for 5 divided by 2 would be 1, right? Because 2 goes into 5 2 times, and then what is left? There's 1 half remaining, right? So the answer should be 1. Alright, that's not really difficult. How about 6 modulo 3? Well, we expect that 3 goes into 6 a whole number of times, so there should be no remainder, so the answer should be 0. And that is exactly the case. How about 11 modulo 3? Okay, so 11 divided by 3, that is the closest integer number of times that 3 can go into 11 is obviously 3, because that should be 9. And then 3 times 4 would be 12, so that's too much, right? So we actually have to stop at 9 and then say, okay, well then there's 2 remaining. And so that's the answer. And so that's really how it works. Okay, before I actually conclude this tutorial, I think we should just really talk about incrementing and decrementing. Okay, and so what that comes down to is, for example, maybe we're going to be writing small programs that need to do this for us, that need to kind of like automate counting in a sense. Then what we would like to do is to actually declare a variable. In this case, I just an integer value 1, I for integer, then I set it equals to 1. But what this next line is actually saying is that we want to add 1 to it, right? So I'm just saying I plus equals 1, and then I print I, and the value that we returned that should be expected here is going to be 2, right? Okay, but there's another way I can do that, but it just has the exact same meaning as what I've just written over there. I take the integer, I set it equals to 1, and then the next line, I increment the original value I started with by 1. Alright, so I write I has now become equals to 1 more than I itself, and then I print that value again. I actually expect the value 2. So decrementing a integer value in a programming language is basically just the opposite of incrementing a integer value. So here I have an example where I set j equals to 3, in other words the integer 3, and I decrement, that means minus equals 2, and I decrement by 2. So if I run this, I should expect a value of 1. Alright, so that's not really surprising at all. I'm sure you can agree. But there's another way I can do this, just as I've done it before. Instead of writing minus equals, I can take j, set it equals to an integer, and then I can say, well, now I want j to be equals to 2 less than what j was. So j is equals to j minus 2, and then print the value of j, and again I should expect a value of 1. Okay, and so I think that's really it for this tutorial. See you in the next one.